All right, I should be good. Recording here. Yeah, we're in business. All right. So the mini exam, people have turned them in. If you're turning one in, please place it here. Shit, more grading for me. Great.
Sorry.
Why do I do this to myself?
You just read 100 on last.
Just, you know what? Take them back here. Everyone gets 100. No, I'm kidding. All right, well, we have class today. What's today? Wednesday? Yeah, and then next week we actually do have class all week, right? But I understand some people do leave Wednesday to go out of town. I will be here. I will record the class. If you can't be here, I'm not going to be, I'll be sad a little bit maybe, but I'll move on. So I'm just letting you know I will be here, right? So next week we'll have a regular week. All right, so last time we were talking, well, we're still in this 13.2, right? Which we've been in now. We're going on day 3, right? So we got to a point where we were computing this thing called work, and I'll put on the board here the main formula we had from last time, that when we're computing the work done, it's equal to the integral over the curve we're moving along C, and then it's the field F dot dr. That's the notation right there for work. Now, that integral doesn't always mean work, okay? If the field is some sort of force field, like a gravitational force or something like that, then it would be work. But it can represent other things depending on the physical situation you're looking at. I think it's most efficient if the first time we see it, we start looking at as work because it's something most of you have seen in physics or some other class. So this is the notation for it, but what does it actually mean? It means we're going to do the integral, the line integral over C of the vector function f, right? That field that we're given or we have to produce, evaluated along r of t. What's r of t? That's the vector function that does what? What is this vector function, r of t? It's the path. This is the path. This is the actual C. The curve C is drawn by r of t. All right? So this r of t is a curve, a vector curve, or a vector function that draws a curve in space. And then we dot that with what? Anyone remember? The what? The derivative of r of t, right? dt. So this right here is a vector, and we're going to dot it with another vector. Now this is in the notes, right? If I just scroll up, it's right here. Whoa. It's right there, okay? It's that formula right there. Now I left it as C over here, but technically this should be A to B because those will be our restrictions on t that draw the curve. All right, and we did 2 examples in class last time. Did we do that one? I think we did. I don't remember that we ever did this one.
I think we did.
Can someone look? Did anyone write this one? We did? Okay. Yeah. All right. So we did that one. And then I showed you this other notation, okay? So this is actually going to be very useful notation for, again, moving on to the next part of this chapter. Remember, if we're given a vector field, that vector field can either have 2 or 3 components to it, right? Either 2 or 3. Now, if it's 3, right, if that field has 3 components, then we can rewrite this integral as this. So this was back before we were doing line integrals over vector fields. We were just doing line integrals over scalar functions. And this is the connection between the two. So if you want to do this, the equivalent thing you could do is these 3 line integrals. The first one's with respect to x, then with respect to y, then with respect to z. And what you're doing is you're taking the 3 component functions of this vector field and you're evaluating those along the curve with respect to x, y, and z respectively and adding up those answers. all right? We won't use this right away. We'll use this later, but this is where it appears in the chapter. All right, so I have two examples for us to do. So this is the problem. You have a 180-pound man carrying a 20-pound tool bag walking up a helical staircase that is wrapped around a 20-foot radius cylindrical silo. What? Okay. So we have this silo, cylindrical silo, and we have a staircase that is wrapped around this, all right, wrapped around this silo, so that the staircase goes around the back side, comes back around, right? Goes around, and how many rotations? It takes 3 complete revolutions to go up. Okay, so we know that this is a 20-foot radius. And anything else?
90 feet tall.
90 feet tall, so it's 90 feet. All right, so we have a man carrying a tool bag, walking up this staircase, going around, getting to the top, right? It says, if it takes 3 complete revolutions to reach the top of this 90-foot silo, then how much work is done against gravity? So how much work is done against gravity? Now, if you've taken a physics class, there's a very simple way to do this problem. And I'll get to that once we do it our way, all right? The way we're going to do it is with this, all right? So we first have to talk about that the fact that work has to be done, right? For the person to actually walk up the staircase, they have to work. They have to do work because they have to move against the gravitational force that's pulling them down, right? So let's first try and figure out what the field is. The field here is going to be gravity. And we are going to look at it like gravity acts straight down into the center of the earth. So our field, F, is gravity, right? And this field will be, what's the vector? We're talking about the force acting on this man. Okay, so yeah, so what you're thinking of is that gravitational field where everything's being pulled into the center, that field. So that's more complicated because that accounts for being in any position. We are looking at just the force going straight into, like straight down. Okay. We're going to say there's not an X or a Y component to this force. It's directly straight down. So what is it? What is your weight? When somebody says somebody weighs 180 pounds, that's mass times gravity, okay? And is that a force? Is your weight a force? Your weight is a force, yes.
Wouldn't it just be 0,
Pardon?
0, negative 200?
0, 0, negative 200, exactly. 0, 0, negative 200 is the field. That's the force of gravity acting on this man carrying the bag. It's a vector, right? As this person walks up, right? As this person walks up this silo, the only force on this person is the force of gravity straight down, right? Now he has to overcome that to go up the silo, yes? So that vector that's pointed straight down is just this vector 0, 0, negative 200, which is the weight of him and his bag, right? If he puts the bag down, then it's negative 0, 0, negative 180. We all agree? Very simple field, right? This is a very simple field. So we have the field. What else do we need to do the work, to calculate the work? The derivative of what? The path. So we need the path. We need to resolve what R of t is. What draws this thing going up the silo. We have to figure out what that path is. So the question now is, what's R of t? Well, I think part of it, let me get my nice picture in here. Here's my picture, right? If we want to draw this blue curve going up the silo, right? Think about, we need this vector function to have 3 components. 1, 2, 3, right? The x and y components we can think about as if we were to be just looking straight down on this thing, right? And my x and y components just need to draw a circle, right? And while the circle's being drawn, the z is going to be going up. So how do we draw a circle of radius 20? 20 cosine, 20, let me give myself some more room. 20 cosine t, 20 sine t. That all right? Okay, you turning in? All right, thank you. All right, so we've got that, right? The only thing left is to resolve the z part. And this is the part most people have trouble with, is figuring out what the z is. So one way you can, there's a lot of different ways you can think about the z part. What you could imagine is that if you unwrap this, right? If you unwrap this spiral, right? If he wasn't walking on a curve, right? If you take the curving out of it and just think of it as straight line motion, then it would look like he's just walking up a ramp, right? Now let me draw this ramp. It would look like this. It would go like this, like that, like that. All right? That's what it would look like. Now, help me out. Do you know anything about that ramp? You know this is 90, right? You know that's 90.
Is the x the circumference?
So this distance from here to here, what do y'all think? Y'all think that's circumference? Yeah, so he went, how many rotations does it take? 3 rotations, right? 3 rotations. So shouldn't this x be 3 of the circumferences of the circle? So that would be 3 times, what's the formula for circumference?
2 pi r.
2 pi r. So 2 pi r is 20, right? So what's that? 120 pi? 120 pi? So this side is 120 pi. You agree? So what we want here is to try and figure out kind of like what this is. This is like a linear function, right? We know the rise, we know the run. So what's the slope of this line? Rise over run. So what's 90 over 120? 120 pi, sorry. What's 90 divided by 120 pi? Just reduce it. 3 over 4 pi? 3 over 4 pi? Just reducing the fraction? Do y'all buy that or no? Okay, now we need to, look, I'm just drawing pictures for you right now. Like I said, there's many ways to approach this. I'm just trying to give you some geometry. Yes?
Would that be the square root if we're looking for the actual?
I'm not looking for the hypotenuse. No, all I'm doing is saying what's the slope of this line, right? What's the slope? So let's back up for a second here. I want us to back up. Let's go back to this and let's talk about our restrictions on t. Right now, if I do this, right, I'm going to go draw a circle in the xy plane with a radius of 20, right? If I let my t go from 0 to 2 pi, I'm only going to draw 1, right? I need to go from 0 to 6 pi, okay? I need to go from 0 to 6 pi. This helps us kind of get an idea of what this last thing needs to be. So this geometry was just to get you to kind of see what we have. If we were to unwrap the path, it would look like this. At the end of it, what we need is this last component. When t is 0, where do we need to be? What does the z component need to be? Where are you at time is 0? The ground, 0, right? And at 6 pi, where does it need to be? Up at 90, right? So you need something that goes from 0 to 90 as you plug in 0 and 6 pi. Any ideas on how I can do that? I need to put something here that when I plug 0 into it, I get 0. And then when I plug 6 pi into it, I get 90. Would this work? If this is the slope, if this is the slope, right? If this is your slope of this line, then what would the equation of that line be? If I just orient it at the origin, let's say. 3 over 4 pi t, right? T? Does that work? If I plug in 0, what do I get? 0. If I plug in 6 pi, what do I get? I get...
9 over 2.
No.
9 over 2 or 18 over 400.
So it doesn't work, does it? Y'all see what I'm saying or no?
Yeah.
So what we're trying to do is figure out if there's something we can put there that when I plug in 0, I get 0. And when I plug in 6 pi, I get what? 90.
So would you say
90 over 6.
Yeah, why don't we do this? 90 over 6 pi t. See, what I'm doing is I'm thinking about what I need to happen, right? I need at 0 for it to be 0, and when I plug in 6 pi, I need it to be 90. So if I put 90 over 6 pi, then if I plug in 0 here, it's 0, right? And if I plug in 6 pi, the 6 pi's cancel, I get 90. Who cares that it reduces, right? Who cares that that reduces? So what was wrong with ours? What was wrong with ours? This slope thing, what was wrong with this? Why didn't, because we almost got that, didn't we? If I multiply the top and bottom by 3, what would I have? 9 over 12 pi? Right? This was off a little bit. Do y'all see how we're off? Didn't it almost work?
off by 10 over 2?
We're off by, yeah, we're off by something. Let me do this because of time. Go back and revisit this triangle. See if you can get to this by rethinking this triangle. But let's not invest too much time because we have this, don't we? I mean, like, we're here. And like I said, there's different approaches. The geometry, though, can get a little confusing. The way that I did it here at the end where I found 0 to 6 pi and then thinking about what I need is probably the cleanest approach. This is a linear function, right? Would you agree that his vertical ascent is linear? Right? As he goes around the stairs, it's a linear progression up. Just in that direction, it's linear. So he doesn't like speed up, slow down. The stairs, we're assuming the stairs are, they don't flatten out and then go steeper and Okay, so can we just continue with this? Yes? All right. Now, we have our R of t, right? We have our restrictions on t. And so finally what we need to do is get ready for the formula, right? So we'll need a derivative. Let's take a derivative. So the derivative of R of t is going to be another vector function. It's negative 20 sine t, and then it's 20 cosine t, and then it's 90 over 6 pi, right? That's it. And think I'm ready for the work now. I'm ready for the work. So the work will be the integral from 0 to 6 pi. Then it's going to be our force. Okay, now this is the thing. We have to do the force, right? The field evaluated on the curve, right? On the curve. But my field contains no variables in it, does it? My field has no, what, x's or y's or z's. It's like constant, 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 which means that it's just that vector, 0, 0, negative 200. And I'm going to dot that with what? This right here, right? Negative 20 sine t. What's going to happen? Do y'all see what's going to happen when I dot these? The only part that's going to matter is the z part, right? The only thing that's going to matter is z part because the gravitational force, the field here, right, is acting straight down. So we have no x or y component. That means these two actually didn't matter, right? And those of you who've taken a physics class know that if you move from somewhere on the ground to somewhere up, How you get there doesn't matter. What matters is the distance you travel, right? And that's what this is basically saying. The path does not matter. What matters is this z component. That's what matters. And that's going to be our distance. So let's dot this. When we dot this, we get integral 0 to 6 pi of what? Gone. Negative 200 times 90 over 6 pi, right? And then what? dt? dt. Now that's all a constant, isn't it? I'm not going to clean it up. I'm just going to leave it like that. The antiderivative of that would be that constant with the t evaluated from 0 to 6 pi. And what happens when you plug in 6 pi? It cancels and you just get negative 200 times 90. And then what happens when you plug in 0? You get 0, right? So what's your answer? Negative 200 times 90, which in a physics class, again, this goes back to what you learned, is that basically the work done would be the weight of the person times the vertical displacement, which is 90 feet. Right? But this is why. This is why that always happens, because of this what we just got here. Okay? Make sense? And then our answer would be in foot-pounds, because we're measuring things in pounds and feet, and length is in feet. Yes?
There's, I remember there's one question to find the, we solved for one question like that on the one of the mini exams, when you give us a point and another point in a line, and we find the distance, right? I don't remember what mini exam was. But there's like a formula, I think it's curvature or something. You remember?
I'm not sure what you're talking about, actually.
I'm gonna figure it out.
Yeah, look it back up and then we can talk about it.
Yeah.
I mean, we haven't talked about work, right? We haven't talked about work. Okay.
I'm talking about which one is the distance. So
Okay. Oh, arc length. Oh, arc length, yes.
It-
Yeah. But we're not finding arc length here, right?
We can find the distance using that.
We could find the arc length. Yes, we could. We could. Absolutely. All right, this okay? All right, now this assumed that we were on Earth, right? And like we had gravity and the person weighed 180 pounds and the bag was 20 pounds, right? But generically, like in the universe, you don't necessarily have to be under the influence of Earth's gravitational force, right? If you're floating in space, okay, imagine you're floating in space and you are not being significantly impacted by any large body around you, then you're just freely floating, right? So look at this next question, because it's an interesting question. This object right now that's moving, I need to be clear, this object is just in space, all right? Like, it's not on Earth. It's not under the influence of any gravitational force. So you have a 10 kilogram object. Now, kilograms is a measurement of what? What's that? Mass, right? And mass and weight are not the same thing, right? An object's mass is a measurement of how much matter is there. Weight is that mass times the gravitational acceleration of the planet you're on, or whatever, right? Once you move away from the planet, your weight changes, but your mass stays the same, right? Conservation of mass. No matter where we are, we should keep the same mass. So that's why this object, I'm giving you the mass as opposed to a weight, because if I give you a weight, then that assumes it's on a planet or something. So we have some 10 kilogram object that's moving through space, and that's the position function. So it's some sine wave, so it's doing some crazy shit moving through. I might have a curve here. Yeah, here it is. That's the actual path of that object, okay? It's weird, whatever. It is what it is, right? So we have this 10 kilogram object that's moving through space and moves along this curve between t equals 0 to 1. So it's going to start, move along, and then stop, right? The question is, find the work done on the object during this time period. So to move that object through, around, what work is done. And what's confusing about this problem initially is that you're like, well, where's F, right? Because you don't have gravity, right? You don't have gravity. Agreed? But there's a very famous equation, right? Newton, one of Newton's laws. What does that law say? Force equals mass times acceleration, right? Okay, so for us, we're going to convert this. It's going to be force is going to be our field equals the mass of the object, which for us is a constant, isn't it? Times the acceleration of the object. How can we calculate the acceleration of this object? The second derivative of its position. So I'm going to, instead of having acceleration as like a constant, a number, it's going to be a vector. And that vector will be the second derivative of the position. So if you give me any object moving in space and you give me its position function, I can always tell you its acceleration function. And then its mass times that acceleration function should be the force. And that would be the field we're talking about here. So let's compute this field. For us, this field will be the mass, which is 10 kilograms, right? Times, all right, now we need a derivative. I should have done that first, right? We need a second derivative. What's r prime of t? Careful with things here. Derivative, not anti. 4 cosine 4t. And then the other one is 8 cosine 8t. And then 2t. Okay, that's our first derivative. Then our second derivative is negative 16 cosine, sine 4t. And then negative 64 sine 8t, and then 2. At least that's a constant, right? All right, so our force will be, or our field, whatever you want to say, field, force. This will be that times negative 16 sine 4t, blah, blah, blah. I'm not going to write it out. Let's go ahead and multiply the 10 through. So our field, right, is the field negative 160, right, sine 4t. And then negative 640 sine 8t, and then 20. So just multiplying, scaling each of those by 10. All right, we've got our field. Our field is already a function of t, right? It's already a function of t. So when I do this right here, right, this field right here, this f right here, I don't need to evaluate it along the curve. I've already done that. This is already a function of t. So we're ready to do work now. Pardon? So the work will be the integral from where? 0 to 1. It'll be our field along this curve, which is the force along this curve, which is this. This right here. Negative 160 sine 4t, negative 640 sine 8t, 20. Dot that with the first derivative, right? The first derivative, because that's the formula. The first derivative is 4 cosine 4t, 8 cosine 8t, and then 2t, dt. And the numbers are going to get ugly here, but I think we're going to have probably some Pythagorean identities in here. I'm guessing we're going to have some sine squared, cosine squares. I'm hoping that'll turn into ones. Maybe not. Maybe not, but that's what I'm hoping for. So this will be integral 0 to 1. Okay, multiply these first two. For negative 640 sine 4t cosine 4t. Okay, that wasn't very good. No, I guess it's not working out the way I hoped. Okay, next one. These two together. Calculator, please, somebody. 8 times 640, yeah, negative.
5,120.
5120, and then it'll be sine 8t, cosine 8t, right? And then finally, 40t dt. Is that all right? All right. So these are definitely doable, like this is doable integral. Because if I wanted to do these, I could do them separately, right? And if I did this one, I could do a basic u sub, right? U would be sine 4t. What's its derivative? Cosine 4t. So I could do a basic u sub here. I could do a basic u sub here as well. And then this one's just power rule. So this is doable, yes? Let's see. Did I do it already for us? I didn't. Okay. Do you trust that you would get the answer? Yes? Okay. We just go to the computer and do that. And that would be the work, moving that object along that curve in space. All right, and that concludes the section, all right? This concludes the section. Oh, you know what? Hold on. I have this. We could have it do calculate for me. Nah, it's all right. We won't. Let's get out of this section. I'm ready to move on. All right, let's move into 13.3. So 13.2 is a pretty big section, right? Pretty important section. There's a lot of stuff in there. 13.3, here we come. The fundamental theorem of line integrals. So you learned the fundamental theorem of calculus, right, in Cal 2? The fundamental theorem of calculus is basically the thing that allows us to take the antiderivative and evaluate to find like an area under a curve, right? So as a reminder, I know you know this already, but in Cal 2, it said if we have some function f, right, on some interval a, b, that if we take the antiderivative, right, of this little f and evaluate that antiderivative at the two endpoints, right, take the antiderivative of this, we'll call it capital F, then if you evaluate the antiderivative at two endpoints, it would give you the area under this curve. This is actually called the evaluation theorem. It's a version of the fundamental theorem of calculus. So the relationship here is that this right here, little f, is the derivative of capital F, right? So now we're going to have this thing called the fundamental theorem of line integrals, and there's something very similar to this